She finished her PhD at EPFL, Switzerland, and after spending 1 year at UIUC, so she joined Google Speech, and now she is a senior staff member at Google Speech and lead a team as far as working on cloud ASR. Internally, she done a lot of great stuff on our cell phone and different application impact worldwide millions users. I'm really happy to have her today. And please, Parisa.
All right. Thank you very much for the introduction. I see some more people might be wanting to join. So just let me know. And I'll go back here. Yeah, so I'm super happy to be here and talk about my work. I was told that the audience is quite diverse, and not everybody knows about automatic speech recognition. So I divided the talk into two parts. In the first part of the talk, I'd like to give you an overview of recent advancements in automatic speech recognition, and then I will talk about remaining challenges and how they relate to industry and the research that we do at Google. Of course, I have to first acknowledge and thank many collaborators, and I apologize if I left out any names. So what is the problem of automatic speech recognition? So assuming we have a word sequence and an audio waveform, the problem is to find the word sequence that maximizes the posterior probability of basically words given audio waveform. And you can write this using the Bayesian rule into a product of an acoustic model and a language model. And the acoustic model is basically talking about or measuring variations in the acoustic realization given some word sequence, and the word sequence is basically trying to say how probable the word sequence is. A little bit more detail, you can think of this as a pipeline of probabilistic mappings. So we have the audio coming in, we do some sort of feature extraction, signal processing on the audio, and then we convert that into a state, which is basically the state of an HMM, which models our duration model. Then we have decision tree that basically groups these states into phonemes, which are the units of sounds. And finally, we have a lexicon that is telling us what is the pronunciation for each word. So basically mapping words to phonemes or phonemes to words, back to words. And a language model that tells what the probability of a sequence of words. Right, so this has been traditionally how speech recognition was done, and the main breakthrough came in 2010 or 11. That's the time where an intern from Jeff Dean's lab, I think, went to Microsoft and showed that the acoustic model can be a neural network, right? And this is really a comeback. It's not completely new work. Neural networks were used previously in acoustic modeling as well. But what made them now very successful was ability to apply it to more data, and there was more compute available, to do the expensive backpropagation that's needed for training the neural networks. And throughout the years, variations in modeling was tried and made improvements, starting from more simple feed-forward networks to LSTMs that are recursive and convolutional neural networks and so on and so forth. Other components in this sort of statistical mapping that I showed you also were updated or neuralized throughout the years, but of course the biggest improvement came really from updating the acoustic model. A more recent breakthrough happened when everything was kind of replaced by an end-to-end model. Basically, the input is now acoustic features, and the output is just words or a sequence of words. Recent work has shown that you also don't necessarily need to do the feature extraction. The input to the end-to-end model can also just be audio waveforms. But most systems that we use in industry still keep the feature extraction because it's cheap and it works quite well across domains. I'd like to spend some time talking about different methods of doing end-to-end modeling in speech recognition. So any kind of sequence-to-sequence problem that you consider, has this problem of solving or addressing differences in input and output sizes or lengths, right? So for speech, we have an audio that when we extract acoustic features from can be quite long, right? And the corresponding output is much shorter. So how do we align these two to make sure that we can model them end to end? And CTC, or connectionist temporal classification, solves this problem by introducing a blank symbol and also allowing different symbols to be repeated and then collapsed during decode time. So, for example, like if a sentence is "this is a cat," the output of that network can be, a bunch of blank symbols, then the words "this" and then more blank, and then repetitions of symbols or blank. The loss is basically sum over all possible alignments between input and output. It's a monotonic alignment between the speech input and the corresponding text. And one feature of this type of modeling is that it makes an independence assumption between the outputs. So the output at time t does not depend on the output at time t-1 and before that. A nice feature of this modeling approach is that it can work in streaming mode. And what do I mean by streaming mode? So basically, as the input is coming in, we want the model to start producing the outputs. We don't want the model to need to wait for the whole input to be consumed before it can output things. And this is very important in industrial use cases. So this is the CTC. It was pretty popular, and it made big changes, big improvements in speech recognition. The second type of architecture that I'd like to talk about is encoder-decoder. First came from the translate world, 2015, I think. So the idea is that, again, you have acoustic features that are encoded to some higher level representation, and you have a decoder now that is autoregressive. So the decoder has access to its previous output as well as access to the encoded input features through an attention mechanism. And this is optimized using a cross entropy loss. It is very successful in modeling short form speech recognition, but one of the downsides of it is that it's not natively streaming. So basically, the decoder can pay attention to any part of the encoder feature, so it has to wait for everything to be ready before it can output anything. So now this final model that I want to talk about is called the recurrent neural network transducer. It's quite interesting because in architecture, it's a little bit similar to the encoder-decoder architecture that I showed you before. But now we have a joiner network that actually is a feed-forward network, and it has access to the encoder and the predictor, which predicts the output. So the predictor is still autoregressive. It doesn't make an assumption about independence of the outputs, so that makes the model more powerful. But also the joiner, basically, because it's just a feed-forward network, can output at any time. Again, a blank symbol is there for us to manage the differences in symbols, and the loss again is sum over all alignments in the RNNT lattice. Again, this is really nice. We like it a lot at Google because it can work in a streaming mode, and it's basically one of the models that we use in our production systems. All right, so I showed you a bunch of recent advancements in speech recognition, and I wanted to show you this leaderboard that shows the word error rate, which is basically the metric with which we measure the performance of a speech recognizer on LibreSpeech. LibreSpeech is a very popular benchmark. It is read speech, so it's sort of like a little bit simpler, and as you can see, the word error rates are kind of low, and the graph doesn't go far enough back in history. It starts from January of 2016, but it shows kind of how things have improved. So it starts with the CTC model. There is a big improvement with the introduction of the encoder-decoder-based LAS systems. And then the other trend that I didn't really talk about, but it's like happening now, and it's very important, is self-supervised learning and basically making use of unlabeled data, and that is also making big differences. So one note about the actual absolute word error rate. So as you can see on the y-axis, we are now below 5. That's basically when people start to say this. We are in the noise section, and even humans may disagree what the exact transcript can be. And there's a lot of talk about now the automatic speech recognition can understand humans. It's as robust as humans, and it's quite accurate. So then the question becomes, what is there for us to solve? What are the main challenges remaining? So from an industry point of view, this is the main problem for us. The system has to work for everyone, everywhere, and all the time. So this becomes kind of a problem of scale. So thinking about the different surfaces and devices where we serve speech recognition. So starting from the cloud or our servers, where we have lots of compute power, we can have a very strong speech recognizer there, but also we have to serve these systems on more compute constrained devices, such as the phone or the watch, or in different cars, where the acoustic realization can be quite different from the room, and the noise conditions are very different. Then, there's the problem of many languages. We have 6,000 languages, I think, in the world, and maybe 100 of them have a written form. But in order to be able to serve speech recognizer across, you have to make all of these languages recognizable. Domain is another dimension in this problem. So in the most simple domains, there's command and control use cases where the vocabulary is very small. Then on the other end of the spectrum, we have search or voice search, where you can have a long tail of words that people want to search for, and the system has to recognize them as well. There's telephony transcription, where there's variations in the audio signal that we receive that can play into the quality of the recognizer, and so on and so forth. So just to give you an example, by the way, I think maybe the animations don't work. Maybe. Okay, so just think of this as without the topic one thing. So I'm giving an example where you have 3 domains and 3 surfaces and 80 languages, and this ends up with 720 models. You may think that you are Google, you can do this, but really this is a lot, and it's just one example. So one of the topics that I want to talk about is multilingual ASR, which basically tries to reduce this dimensionality here. All right, so the second topic that I want to talk about is basically data selection and efficiency in data. So as you probably know, if you've followed machine learning advances, a key to the performance of many of these methods that are in use right now is availability of in-domain data and supervised in-domain data. But this is expensive, not necessarily always available in all domains. So people have come up with self-supervised learning, which makes use of unlabeled data, and there's more access to that. But the question is, can we still do better than just training over unlabeled data, or what kind of data should be used in self-supervised learning? And I'll talk about that as well. The third topic is just the trend of talking about optimizing different tasks. So far we talked mainly about automatic speech recognition, but there's speech-to-speech translation, where the input speech is in language A, and the output should be in another language. There's spoken language understanding, where traditionally a pipeline system has been used. So we first do a speech recognition. We first use a speech recognition system to get the transcripts. The transcripts get consumed by a downstream NLU system, which basically parses that into intents and arguments. And if you think of your, virtual assistant use cases, this is very relevant there. And the final topic that is not shown here because it's covered by this big yellow thing is actually voice conversion. I want to show you a video. Hopefully this video will work, of Project Relate, which talks about basically end-to-end speech conversion. Let's see if this works. Oh, look, it does. How do I make the audio?
Communication is a fundamental human need, and I think it's also a basic human right. I'm Haghani, a brand manager at Google. More specifically, I'm a namer, and it's a lot of fun to say that I'm a professional namer. I had a type of muscular dystrophy that affects the way I speak. I have always loved making new friends, but when people can't understand me at first, they have trouble getting to know me. It's as if there's an invisible barrier between us. I believe technology can help bring down that barrier.
My name is Julie Catio. I'm a product manager at Google in the research team. Project Relate started in 2018 when we realized that our speech recognition technology could be improved to help people with speech impairments be better understood. Standard speech recognition doesn't always work as well for people with atypical speech because the algorithms have not been trained on samples of their speech. So we decided to create an app that would be custom trained on individuals' unique speech patterns.
We named the app Relate because of what it enables you to do.
To use the app, the first step is to record a set of phrases so it can get to know how you speak. The Relate app has 3 built-in features: Listen, Repeat, and Assistant. Listen transcribes everything you're saying in real time.
So I have a custom voice model now.
Repeat repeats what you've just said in a clear computerized voice.
That's kind of hot chocolate.
Gotcha.
Thank you.
Assistant connects directly with your Google Assistant.
Take a selfie.
Okay, get ready.
I hope I live to see the day when disabled people can move through the world and expect the same level of connection as everyone else has. I think Project Relate is bringing us closer to a better future.
Okay, so yeah, Project Relate is basically an end-to-end, thank you, speech-to-speech conversion system. I'll tell you a little bit more about the architecture behind it as we go through the talk. All right, so now let's first start with multilingual speech recognition. Multilingual speech recognition has become much easier with the advent of end-to-end models, because now instead of having to unify an acoustic model, a pronunciation model, a language model to arrive at a multilingual speech system, you can think of just unifying an end-to-end system, which is much easier also to train. So there's lots of new work happening in this space. It's useful because it benefits multilingual users. The idea is that the model can learn shared representations, which can help languages for which we have lower resources, less amount of training data available. And then in terms of training and maintaining and serving models, it's obvious that it reduces those numbers and helps with maintainability of the system. But there are several challenges, of course, with speech recognition. Mainly, the different languages or the different tasks will compete for capacity. So as we add more languages to the system, you need to also add capacity. And usually, high resource and unrelated languages may see degradations as there is inter-task conflicts during the training time. One other interesting challenge comes from code switching, where a user can switch between different languages in one sentence, and how to address that. So I'd like to cover a few solution flavors that we worked on for multilingual speech recognition, and I'll start with introducing language-specific structure into the architecture of the network. So this work, we called it mixture of informed experts, and it basically introduces an informed expert layer into the neural network. It is very similar to just mixture of experts. So basically you have one expert per language, but the idea that we the intuition that we had in this work is to tackle the conflicts that can come up with between the different tasks, meaning between the different languages, by eliminating gradients from other expert parameters. So we have a bunch of training data from different languages, right? And we know the language ID of the utterances within our training data. So that information is used to basically guide the backpropagation, and I will talk a little bit more about that, to eliminate gradients. And that's why we call it informed experts. So the experts are informed about, you know, the data that they are being trained on. So during the forward propagation, there's the model is in collaboration mode. So assuming that you have layer inputs to your informed expert layer, these are fed to all the experts. So each of the languages gets its own expert, and we also, you know, experimented with having a multilingual expert in the mix. And the output of this layer is a convex combination of the outputs of all of these experts. The weights for the combination comes from a gating network that, you know, can have different architectures. So the basic architecture of the gating network just takes in the language ID. You know, it can learn an embedding on the language ID, or it can be just a one-hot of the language ID to basically assign weights that get propagated to the next layer. Or we can try to get rid of this knowledge from language ID during inference and try to just estimate it using the layer inputs. And I will show you how each of these methods work. During the backpropagation, this is where this method is different from mixture of experts. We exploit structure in the data, which is basically knowledge about the language in the training data. So assuming we have an utterance from language A, during backpropagation, we only backpropagate through the language A expert and the multilingual expert. And the hope is that we eliminate some of the conflicts that can come up during multilingual training with this method. Okay, so these are the results. Let me first explain the set of languages that we considered. So these are the dialects of Arabic, plus English and French. The idea is that in our setting, at least, Arabic is a low-resource language. So combining all the Arabic dialects should, you know, benefit all of them. But English and French are high-resource languages. We have a lot of data, and they don't necessarily relate to Arabic. So there might be degradations in performance when we include them in the set of languages that we experiment with. So the first column is showing you monolingual word error rates, you know, the performance. And just so you remember, we want to have lower word error rate. When we train a multilingual model on this set of languages, the Arabic languages improve as expected, but French and English degrade a little bit. And if we use mixture of informed experts, we see that actually the degradations go away on English and French, and Arabic also improves a little bit more than before. Now, as I mentioned to you before, the gating system takes the language ID or the Oracle language ID as input. And this may not be available at inference time, because we want the system to be producing output in a streaming fashion. So you can't first, you know, predict the language ID on the utterance and then feed it to the network. So we experimented with learning the language ID implicitly during the training. And it turns out that using an LSTM gate was sufficiently good for this purpose, and it overall matches results with when we feed in the Oracle Lang ID, which is what we're after. All right, so the second topic that I want to talk about is basically distillation. So in the previous method, we are adding structure to the network, and we are also increasing the capacity of the network by adding this language-specific parameters to the network. But we may not want to always do that, because maybe the network that we want to deploy has to be small enough. And one of the approaches that we consider for doing this is actually using monolingual models that already exist and distilling from those into a multilingual student. So in this setup, we are assuming that we have per language teachers and teacher models, right? And then we have, of course, training data from each of these languages. So we have ground truth. We can compute the ground truth loss for each of these input examples. And the challenge mainly becomes how to combine all these different losses, because it turns out that the network is quite sensitive to how you're combining the distillation loss and ground truth losses together. The method that we came up with and we called self-adaptive distillation is to make the weight of the distillation loss depend on both the teacher and student's ground truths. So in high level, we basically take into account how confident the teacher model is on any example, and similarly, how confident the student is on any example, and use this information to weight the distillation and ground truth losses. And this works quite well across different languages. Of course, the downside of this method is that we are assuming that we have the monolingual teachers available to us. It turns out the teachers can also themselves be multilingual. So if you have a group of languages like Arabic that can simply be pulled in together and trained together, you can use that as a teacher. In this particular example, sure.
So how many data is for the Danish?
Danish is actually lower resource in this setup. So I was just gonna explain a little bit the setup. So this is basically 5 languages that we refer to as Nordic. They are not really all just Nordic languages. It's Danish, Swedish, Finnish, and I think 2 more languages that are in the setup. These are all low resource languages. And then we add English, which is, a high resource language. And you can see the baseline basically is just the vanilla multilingual system, which we get a order rate of a little bit below 11 on. Then when you do distillation without the simple distillation, with just summing up the distillation losses and ground truth losses, you get some improvements. But then with self-adaptive distillation, you can get lower. The nice benefit that is additive here is that if you combine this method with adding capacity, we still get more gains. So it's something that we currently use in our production systems to improve the multilingual models that we have.
Yeah, the following question could be, now we see an impressive result from the teacher-student learning on RT, but does this effect also based on the language? But like which German language or Latin language, that those things related? Or
yeah, that's a very good question. So we've tried it on a variety of language groups. We haven't tried this method on very, very large language groups. It has been mostly like clusters of languages that are somehow related, combined with English, because that's the main use case for us. But it's a good question, and we are considering trying those things as well.
it's really impressive to see the result. It's almost but
yeah, so like you go down from a little bit. The graph is also kind of showing it as a big change, right? But the absolute order rate maybe is not as big, right? You go from 11 to 9,
yeah.
And then capacity increase always helps. I will show you a little bit more about that. All right, so this is like a great segue, because we talked a little bit about I think maybe you expected me also to talk about this because I'm from Google and we have to talk about large scale things as well. So let's do this now. So this is another work done by Bo, who was the Hawk's host, I believe, right? So here the setup is different. We have 66 languages. That's like 600 million utterances. And then if you want to know in terms of hours of data, this is 670,000 hours of data. The chart or the languages are divided into 3 groups. Like first is like 15 languages specified by the yellow-orange color, and then we have the 32 languages that include those 15 languages. So think of orange plus blue, and then finally everything together, which is 66 languages. And this figure is showing you hours in log scale for each of the languages. And as you can see, it's quite variable and quite diverse in terms of the number of hours that we have available. So what we want to study here is the connection of model capacity to how things perform as we add more and more languages to the system. What we know from previous studies is that larger models tend to have better quality and also faster convergence, which is great. The models that we considered in this work are 400 million parameters. At the time, it sounded even more when we were doing this. Like when we went up to 1 billion parameters, it sounded really impressive. But now 1 billion is not such a huge model. Although I would say that still for serving such a model, we have a lot of challenges. Anyway, so the way to blow up the size of the model, usually what works best is to increase the size of the encoder, make it deeper and wider. The decoder doesn't play a big role in performance, so we keep the decoder size fixed. And this is how we achieve the different sizes of the models that I will talk about. All right, so let's look at the quality on a single language. The setup here is we train 4 different sizes of models on the 3 set of languages that I showed you at the beginning. And then this graph is showing the performance of one single language, which is EN-US, English from US. In summary, again, the larger model is performing the best. And as we add more and more languages to the setup, quality decreases. So like if you look at this graph, in particular in the orange or the yellow line, is the best quality for EN-US, right? It is decreasing in terms of word error rate as we increase the size of the model. But we can never achieve the same performance on EN-US as we increase the number of languages, even though the size of the model is quite large. It's 1 billion parameters. So similar trends are seen for the average word error rate on the set of 15 languages as well as the 32 languages. So this basically, the motivation motivates us to see whether we can use pre-trained models to improve the performance. And pre-trained models have been used widely in semi-supervised or self-supervised learning or for domain adaptation, but here we use it for just supervised learning. And the setup is we start with the larger model, the largest model, the 1 billion parameters model, and we continuously add more languages. So we first train it in 15 languages, get it to convergence point, or it doesn't really have to get to convergence, but it has to do some steps. Then we start adding more languages. And of course, one detail that I left out is how do we add more languages, because the input layer actually is language dependent. We pass to the input layer the language ID of the utterances as we are training them. So if we want to add more languages, then that input layer has to be dropped and has to be initialized randomly again. And similar issue we have with the output layer, because the output layer is basically the union of graphemes from all of these languages that we are considering. So we start with 15 graphemes from 15 languages. We train the model, we drop the output layer, reinitialize it with graphemes with a much bigger size output layer, which now covers 32 languages and so on and so forth.
But ultimately, there's one output layer.
There's
And
one
it'll
output layer.
spit out one of 32 languages.
Exactly. Yeah. So then this result basically shows you what the performance looks like. So the first row is monolingual word rate. So if you train just on each of these languages a monolingual system, by the way, this is a very expensive experiment to do because we had to build 66 models. Yeah, so what is the performance there? If you now start training a 1 billion parameter model, that's the second line, initialized randomly, what is the performance on each of the set of languages? So in US, degrades from 4.6 to 5.3, and similarly, the other languages also degrade.
Just a follow-up question from Justin. So how big is the vocabulary size in terms of tracking?
That's a very good question. I think for the 66 languages, we go up to 16,000.
Wow, that's a lot.
Yeah, well, when you add the Asian languages, the number of graphemes basically increase. We also have to prune out some of the rare, symbols from Asian languages.
So is the graphene what comes out, like, I guess, probability distribution?
Yes.
of the graphene?
Yes.
But that would cause a mixing of the character sets of various languages.
Yes.
So since you already are using a gating unit earlier with the exports, can't you make use of that to somehow choose the
Which-
character set because we have a probability distribution?
Yeah. So the training data is mostly monolingual. The training data does not mix different languages. So because the model is trained like that, it doesn't really get confused to output a symbol from another language. It might start outputting symbols in the wrong language if you condition it with the wrong language ID. But we are cheating and we are giving the language ID to the model. So the model learns that if I give it English, it has to basically just limit its output to the English graphemes.
But then how would it handle in the case of code switch speech?
Yeah, so we are not considering code switching in this setup. That's a very fair question, but yeah, I can tell you a little bit about how we do code switching as well. It's quite interesting. Yeah, so back to the slide. We go to the next one actually. So this just basically motivated a little bit more staged training. We start with 15 languages. The model is initialized from scratch, and then for adding the 32 languages, we initialized from the model that was trained with 15, and then so on and so forth for the 66 languages. And this table shows you the results. The nice thing is that now we can match the performance of monolingual, or get a little bit more improvements over monolingual systems, and it is a lot less expensive to do this. And from an industry perspective, this is important for us, because if we train the model on subset of languages and later on we had more languages to train on, this will help us really not to throw away the work that has been done before, and reuse the model from before, and also get extra performance gains. Okay, so I just want to, I don't have slides about code switching, but because there was a question, I just want to quickly talk about it. We think about code switching in the context of Indian languages a lot, because that's where code switching happens very inherently. So we actually call our English from India system Hinglish, because Hindi and English are code switched together a lot. So one of the approaches that we considered for code switching in particular is basically eliminating or separating the problem of rendering from the problem of predicting what the output should be like, right? So, again, thinking about English, we have the English script, the Latin script, and we also have Devanagari, right? So we normalize the training data, and this is the hard part, to transliterate everything to the same script. So if we have mixed English and Deva, we will just transliterate everything to English, and this is not completely trivial to do, because if you write a Deva word in English, you can write it in different ways, right? And we have to basically have ways of normalizing everything to the same space.
Wouldn't that cause issue with the vocabulary? Because like the transliterated words might not have any meaningful word piece to correspond to.
So now if you think about this method, the output space is just English, right? So all of our training data is in English. We will output English, and then outside the model, we will convert back to Deva. That's one of the approaches that we considered. Sure.
What if in some language there are no similar sounds in English? How do you normalize the data?
Yeah, that becomes more difficult when we go to other languages. So that's why I gave the example of Deva and English, because we do have data like that, and we can learn models that do this transliteration. But it's an open question how to do it for other languages. Sure. Do I only have 10 more minutes?
You have more.
We have more. Okay.
You have more.
Okay.
No
All
worries.
right. Okay. All right. So
Also, one to follow. So this transliteration model is separate from the speech-to-text model. Like, is it trained separately, or is it also in the end-to-end pipeline?
right now it's separate.
Oh.
Yeah, right now it's separate, but we are working on, again, like the trend is like optimizing different tasks together, but the production system right now is separate. Okay. So we talked about multilingual speech recognition. The second topic is data selection. And data selection in the context of actually self-supervised learning. So self-supervised learning, again, is like the big trend happening in machine learning right now, as well as speech recognition. And the idea is that we learn useful representations from unlabeled data using a proxy task. And the problem has been very well studied, but one thing that we wanted to discuss in this work was what kind of data should be used for training a self-supervised model. So the setup or the goal is that we're assuming we have some data from a target domain T, and we have a big general pool of data G, and we want to know whether we can select data from this big pool and improve the performance on the target domain. So, related to this, there's always confidence filtering that has been very successfully applied to different parts of speech recognition. It mainly removes transcripts that are low quality, right? So we have a teacher model that, labels the data, and then it has a confidence score of how good those transcripts are. And if they are not good, it throws it out and uses the data like that. However, we don't want to use something like that, because for confidence filtering, we need data for labeling the confidence, for the data that has been labeled to train the confidence model. And we don't necessarily just want to think about the quality of transcripts, because really the self-supervised methods are not dealing with transcript quality. They're just looking at the audio and acoustic similarities between different data points. So the intuition here is that we kind of use the quantizer in the SSL work, because speech is continuous in space, right? And part of the any self-supervised learning converts this continuous space into discrete space by quantizing the audio and learning, a vector quantized representation. And the intuition is that we think that some of these VQ codes can capture acoustic characteristics, and maybe we can use these acoustic characteristics to choose data that is similar to the domain of interest. So, we have the quantized code from the system, and then we can apply any kind of text-based data selection method on that. And in this work, we use contrastive language modeling approaches. So we have a general pool of data. We get the quantized code for each input from that pool. We train a language model now because we have discrete tokens. We can treat them as text, and we train a language model on that. Similar thing for the target domain data, and then we compute the contrastive loss between them, and we select the data that is lower in score. So basically, data that is similar from the target domain to the general pool. This is basically saying what I just said. So the experiment setup, again, we have LibreSpeech, and we want to improve performance on LibreSpeech. Yeah, I know that LibreSpeech is already kind of low, but still it's the benchmark. And additionally, we have multilingual LibreSpeech, French, German, and Spanish in the set as well. And the general data pool is YouTube, where we have lots of unlabeled data. We apply a language ID model. We select data in English, French, German, and Spanish, and we will assume that we have 1 million hours of data available per language. So we want to see whether using all of this data works better, or selecting from this 1 million hours would work better. So applying this method on YouTube data based on the target domain of LibreSpeech, how does it sound like? I think I mentioned that LibreSpeech is mainly read clean speech. So this is basically, okay, let's see if I can play this. Okay, it looks like I have to request access. Anyway, so basically, I can't play this, but with lower scores, we actually can select data that is cleaner and is closer in domain to LibreSpeech. And as the score grows, data becomes noisier and less similar to LibreSpeech. These are the performance results of the multilingual setup. So we select 6% of the general pool. So we had 1 million hour per language, right? And we had, I think, 4 languages. So we just use 6% of the data and compare that to when all the data was used to pre-train the system. And we see quite some good improvements because likely we can, we can select data that is more similar to LibreSpeech for pre-training. And these are results for LibreSpeech itself. So if we use all 1 million hours of data without any data selection to do self-supervised learning, we get a performance of border rate 2 and 3.9 on test clean and other. With random selection, again, like 6% of the data, we get some degradation. And you can see that already there is a lot of replication and duplication in the data. We don't really need 1 million hours of data to achieve the performance gains that we had before. With confidence training, you can see the improvements. Of course, confidence training is cheating because it's assuming that we have access to labeled data. And with our method, we can get better performance improvements. And I think this was state of the art when it was presented for LibreSpeech with self-supervised learning. Okay, so I promised I will also talk about speech-to-speech conversion. So the goal is is to improve verbal communication for people who have speech impairments. And Patron was developed with that goal as a end-to-end speech conversion tool. It takes speech from a speaker with atypical speech, and then it basically converts it back to synthesized speech. And I want to play this demo because I really like this demo because it shows Dimitri, one of our colleagues. And Dimitri, he was born in Russia to Russian parents, and he's deaf, and he learned to speak English as a teenager, basically using Russian phonetics. So he transliterated English back to Russian. He read the Russian sort of script, and he learned to speak English like that. So his speech is quite distinct from the variety of speech that we hear, and you can see how he sort of interacts.
Sorry, I'm not sure how to help with that yet.
Can you hear
I'm
it?
not sure how to help with that.
No.
Southern University and A&M College is 645 miles away from Missouri.
Okay. Let me go back.
Sorry, I'm not sure how to help with that yet. Sorry, I'm not sure how to help with that. Southern University and A&M College is 645 miles away from Missouri. Here's the definition of rain. Moisture condensed from the atmosphere that falls visibly in separate drops.
What is the definition of food?
Hey Google, what is the definition of rhythm?
Here's the definition of rhythm. A strong, regular, repeated pattern of movement or sound.
Yeah. So, and on the left, you see Fadi, who is actually, one of the inventors of the Python model. So let's look at the architecture. As input, we give to the model the spectrogram. This is the first version of the model. I think it had LSTMs encoding the spectrogram, and then it had a decoder, spectrogram decoder that basically converted back to synthesized spectrogram. We found that adding a secondary task of also recognizing the phonemes helps a lot. And the model was also updated to be transformer based recently. This model is basically trained in 2 stages. In the first stage, we train it with typical speech, because we have a lot of data from typical speech. And then once the model has been trained, you fine tune it over the speakers that have atypical speech. And it works quite well, but then there's a problem of how to scale this method to many users. And for this, we use residual adapters. Residual adapters are basically added to the encoder network between the layers that we have. And the residual adapter is basically just a down projection, then a non-linearity, which we use ReLU here, and then up projection back. And the very nice thing about it is that the number of parameters that you have to train is super small. So we keep the base model frozen, and we just train these residual layers with the data from the speaker. And instead of having one model per speaker, which is very difficult to maintain and serve, we can then have just sub-models per speaker that we have to maintain. And because the number of parameters that we are training is super small, we can also load them dynamically based on the request and with not too much latency, which is something that we need to care about when productionizing things. There's more about even scaling to more users, because we don't want to maintain one submodel per user, and then it becomes very similar to the expert system that I mentioned to you before. So we learn an embedding based on the speaker ID, and we combine different residual adapters using weights from this embedding and just maintain that instead of per language residual adapters. Yeah, so this is, I think this is basically the last slide that I wanted to cover. And in summary, we talked about recent advances in automatic speech recognition. The big trend is towards large-scale and multitask models, multilingual speech recognition. Data is important, even though we are in the industry and you may think that we have a lot of data, but we have to care about all domains, and we don't have data for all domains. And I talked a little bit about things other than speech recognition, including speech conversion. So if you have any questions, I'm happy to answer them.
All right. I have friends. But Justin is leaving, so let's have a photo right now.
Oh, okay.
Yeah.
Oh, okay, perfect.
Where should we